Okay, so it's a great pleasure to introduce the second speaker of this morning session. And it's Dustin Clausen from Copenhagen University. And he will talk about the close relation between, I suppose it's algebraic K-theory and TC theory, which is topological cyclic theory. Okay, Dustin, yours.
Thank you. Thank you very much for the introduction, and thanks to the organizers for the invitation to speak here. I'm very happy to have the opportunity to address a different kind of audience than I usually talk to, and I hope I don't abuse the kindness you've shown me by inviting me. Yeah, what I'm going to talk about is mostly the contents of this first paper here, but I may also mention some consequences which were derived in these other papers here. So I just wanted to have these references up there at the start for anyone who's interested in looking at the details, because I will be mostly trying to give an impression rather than too many precise details. And yes, indeed, the subject for us is algebraic K-theory. So we're going to pretend, we have to all right now pretend to be interested in algebraic K-theory. So the algebraic K-theory takes a ring and it outputs, well, the first approximation, it outputs a series of abelian groups called the, well, higher algebraic K groups. Or of course, K0 is the most familiar one, the Grothendieck group of finitely generated projective R modules. But in fact, and this is kind of important for the results I'm going to discuss, experience shows that it's rather better to consider a finer invariant, which is the so-called algebraic K-theory spectrum. And these abelian groups for n greater than or equal to 0 are derived from this spectrum by just taking homotopy groups. And there's a philosophy that it's better to work at the spectrum level as far as possible and kind of only pass to homotopy groups at the end. Because there's a lot of operations you can perform here that are nice and do good things that, well, you can't directly do to the homotopy groups. And let me give one example of that, which again is going to be important for the rest of the talk. And that's so mod P homotopy groups of a spectrum, say. So, well, if you have a spectrum X, and just if you're not familiar with spectrum in the sense of algebraic topology, homotopy theory, you can just think of it as some kind of object which is a receptacle for its homotopy groups, which are abelian groups. And the precise details of what it is, what it means are not so important at the level at which I'll be discussing things. But the mod P homotopy groups, first, what they're not is you don't take the homotopy groups of X and then mod out by P. That's not what they are. Instead, you take the spectrum and mod it out by P and then take the homotopy groups. So what's the difference? Well, how do you mod out a spectrum by P? You look at the multiplication by P map from the spectrum to itself, and you take what's called the cofiber or homotopy cofiber, write that as X mod P, and then you take the homotopy groups of that. And what's the difference? Well, the difference is that what do these look like? Well, there's a long exact sequence on homotopy for any cofiber sequence of spectra. And what you find is that the homotopy groups of X mod P are an extension of the naive thing, the mod P reduction of the homotopy groups of X, by the P torsion in the homotopy group in 1 degree down. So it's kind of a, yeah, this is kind of how it works. But it's a more flexible construction than simply taking the mod P reduction of the homotopy groups. And one measure of this extra flexibility is the following fact. So if you have a map of spectra such that the induced map from X mod P to Y mod P is an equivalence, then you automatically get that this lifts mod all powers of P. So if you take mod P to the n in the same sense, oh, sorry, Y, then that's also an equivalence. And in fact, you can even pass to the limit, and it's even, well, these are all actually equivalences, that the sort of p-adic completion of the spectra are the same. So, and it's, yeah. So I'll be phrasing lots of things in terms of things mod P being equivalences or what have you, but it's always equivalent to saying that somehow it's a p-adic equivalence when you, in some sense, p-adically complete the spectrum. Now, there's lots of things that the mod p information for all primes p misses. And what is missed is precisely what is contained in the rational information. And the rational construction is a little more naive on homotopy groups. The homotopy groups of the rationalization are just the homotopy groups rationalized. So that kind of the rational information is completely lost when you look at mod p homotopy. So that's the kind of thing we'll be leaving behind. Okay, so that was just a little preliminary on the kind of world we'll be inhabiting. Now the talk is called the close relation between K-theory and TC, but the first thing I have to explain is that this is a lie, that in most situations, algebraic K-theory and TC are extremely far apart. So you have to restrict the context appropriately in order to have any chance of having a close relationship. So for example, if R is a Q algebra, then TC, this is just negative, how is it, HC minus, minus of R over Q. And well, K-theory of R is, well, algebraic K-theory of R. And there's a map, but it's very far from an isomorphism. Even in the base case R equals Q, this has homotopy in positive degrees, this only has homotopy in negative degrees, so only the degree 0 information matches up. And of course, in higher degrees, you do get information, you get a theorem cohomology class and the data of the correct level in the Hodge filtration with which it lives, but it's still extremely coarse information. This map destroys a lot of K-theory here. So that's one reason why they're really far apart. In the rational case, notwithstanding this Dundas-Goodwilliam-McCarthy theorem, which we heard, which says that if you perturb the rings slightly, then the difference doesn't change. But well, the difference between them is quite large. So, but another related remark is also with finite coefficients. So this, yeah, I could also rationalize, and it doesn't change the fact that they're very far apart. But also with finite coefficients, you have to be aware of something, that if 1 over p lies in R, so if R is a Z bracket 1 over p algebra, then TC of R mod p is equal to 0. So then there's no mod p information. And more generally, TC of R mod p is always going to be the same as TC of the p-adic completion of R taken mod p. So TC doesn't see the difference between a ring and its p-adic completion, whereas K-theory very much sees the difference between a ring and its p-adic completion, even mod p. So this is a big difference. Well, by the way, I haven't yet explained what TC is, but I can already say why there's a difference in these behaviors here, and this will give some idea of how TC behaves. Well, it's also a feature shared by ordinary cyclic homology and so on, so it won't be so unfamiliar, I suppose. But basically, TC, the difference between TC and K-theory, well, this is at a very coarse level, yeah, but this is constructed from TC of R, sorry, I should be over here, is constructed from R as an additive group, you could say. And then you take tensor products and you do some stuff. But it's basically constructed from R as an additive group, whereas K-theory of R is constructed from GLN-R as a multiplicative group. And so when you take this kind of thing mod P, it's if R mod P vanishes, then this guy's going to vanish. Whereas for GLN, for matrices, it tells you nothing about how matrix multiplication should vanish. So that's the reason for the different behavior here. But what the conclusion of this remark is that we can only hope for a close relation if we take mod P coefficients and look at p-adically complete rings. So that is the only setting in which you could possibly hope that these two theories are actually close to each other in reasonable generality. And what I'd like to explain in this talk is that indeed, at least if R is commutative, then they are in fact very close in this regime here. So let me And so it's going to be, so the fact that they're close is going to be based on the fact that they're close in a particular example. So for smooth algebras over FP, and this was follows from work of Geisser-Levine and Geisser-Hesselholt. Well, roughly, Geisser-Levine understood mod PK theory, Hesselholt understood mod PTC theory, and then Geisser-Hesselholt put the two together and saw that they compared appropriately. I can just say that, so if you look at K theory of such a guy, mod P, you want to understand the homotopy groups, there's a spectral sequence. This is a little technical, but it's just to give you an idea of the flavor of the results. So going from the Zariski cohomology of a certain sheaf called mu n, whereas for TC, there is a spectral sequence going from the Étale cohomology, but of the same sheaf. So that, and then there are natural maps and maps of spectral sequences, just like you'd expect. So the sort of the underlying information is sort of the same in both cases. You just extract the information from it slightly differently. So we're gonna, our main result was a relative result, somewhat similar to the Dundas-Goodwin-McCarthy theorem, which says that if you're close for certain algebras, then you're close for other algebras. And I'd like to explain then, I'll state the result, and then I'd like to say something about how it shows that already just this basic case, smooth algebras over FP, implies them being close there implies that it should be close basically everywhere. So the formulation for the relative result is based on the concept of a Henselian map of commutative rings. So I'll put the definition here. So a homomorphism from R phi from R to R prime is Henselian. So these are commutative rings. Well, if first of all, so phi should be surjective. So I could equivalently encode it in terms of the ideal. This is the usual terminology. A Henselian pair is a pair consisting of a ring and ideal such that R mapping to R mod I is Henselian in the sense I'm going to explain. And here's the important condition. So if you take any polynomial in one variable over the ring, and you take any root over R prime, which is a simple root, which means when you take the derivative of the polynomial and evaluate on alpha, you get a unit. Then there exists a lift alpha tilde in R to a root. So any simple root.
You are missing a phi, I think, on the right. You are missing a phi.
Phi? Where?
Because you say alpha in R prime. Oh no, F.
Phi of alpha should be equal to phi of alpha tilde should be equal to alpha.
Mm-hmm.
Yeah. So it's any simple root mod I lifts to a root in the ring. That's the condition. So let me start by giving a geometric example, which sort of plays no role in the rest of the talk, but at least we'll put a picture in your mind, which I think is the correct picture also in the relevant algebraic examples. Well, let's say you have if you have a manifold M and a smooth submanifold N, then you could take R to be the ring of germs of smooth functions in a neighborhood of N, and you can take R prime to be the ring of smooth functions on N. And then the natural map is just restriction. And the Henselian condition essentially is just the implicit function theorem. So you can solve for this thing on here, then you get a solution on a small neighborhood as well. And this is kind of a good picture for what a Henselian map is in general. But let me give the more relevant algebraic examples. So if, well, so So if you have a,
Yeah.
if you're in this situation and I is nilpotent, so I to the n equals 0, then you're Henselian. Well, you can, this is actually sort of the classic Hensel's lemma or Newton method that you can, the problem of lifting along a square zero extension can be reduced to a linear problem, and to solve that linear problem, you just need to invert
so you mean this wipes out the difference between Zariski and et al. In a way?
Yes, in a way. So, or more proper to say Nisnevich. I'll come back to this
okay.
a little bit later in the talk.
But you mean this is then why the two things agree? I mean, okay, fine.
We'll see later in the talk. Yeah. So a nilpotent extension is always Henselian, but also yeah, you can pass to the limit, and if R is iadically complete, then R is Henselian. So you just lift mod every power, the root mod every power, and then you get a root in the completion. So that is, I guess, Hensel's lemma. Then there's a more sort of theoretical example, but it's maybe the most important property you have. So if you have an arbitrary I inside R, well then of course R mapping to R mod I is not going to be Henselian, but you can always what's called Henselize it. So you can make a map to you can make a map from R to R Henselized such that this thing is Henselian. And the way you do it is you just add all the roots that are supposed to exist, formally adjoin them, yeah, one after the other. So in some sense, it's similar to the construction of an algebraic closure of a field, but in another sense, it's quite different. So for the algebraic closure, you have to make to choose an algebraic closure, you have to make arbitrary choices because you don't know how to select roots, yeah? But in the case of the Henselian lifting problem, if a root exists, it is always unique. And this rigidifies the whole construction. And in fact, the Henselization is completely canonical. There's no choices required. And it is kind of an étale neighborhood of the closed subscheme cut out by I. Yeah, exactly. Or in d'étale neighborhood. So it's a more refined thing, or well, I don't know whether to say more. Yeah, it's more refined than the completion. So you can also complete along I. That gives you a Henselian thing. But this guy has much more sensible algebraic properties than this guy here. So the difference between this and this is easy to control because this is just built by adjoining roots, whereas the difference between this and this is often quite hard to control, especially for K-theory. Yeah, K-theory of inverse limits is a really hairy problem. So it's kind of a replacement for the completion. It's a decompletion of the iadic completion, which has more favorable algebraic properties, better formal properties as well. Okay, so that's the nature of this Henselian condition. Now I can state the theorem. Well, sorry, one more definition. So let's define, I think this was already mentioned by Björn in his talk. So we'll just define K inv of R to be the difference between K theory of R and TC of R. So we're trying to see that this has to be small. So the theorem is, so again, yeah, the homotopy of this will sit in a long exact sequence with the K groups and the TC groups. Okay, so the theorem is that if R to R prime is Henselian, and P is an arbitrary prime, then K inv of R mod P is the same as K inv of R prime mod P. So there's, I guess, a couple of ways to read this. So one way of saying this is that if you know TC of R prime, TC of R, and K theory of R prime, then you know, well, I should say mod P. Let me implicitly, I'll mean mod P. Then you know K theory of R. So that's good. You can imagine you can understand TC, although, and if K theory of this potentially much simpler ring tells you K theory of this ring here, at least mod P. Another way of saying is that yeah, well, it's exactly what it says. So if K theory and TC are close for R prime, then they're close for R. In fact, they're exactly as far apart. Yeah, that's what the theorem says. Okay. This theorem has some special cases which are worth highlighting. Well, one is when in the nilpotent case, then this is the mod P Dundas-Goodwillie-McCarthy theorem. For commutative rings. So theirs is a general theorem without mod P coefficients for associative rings with this nilpotence condition. So we recover a certain specialization of that. Another special case, which diverges from the theme of this talk, but is nonetheless quite interesting, is where 1 over P is in the ring, R. Well, then all of the TC terms vanish. So TC R mod P is TC R prime mod P, they're both 0. And the conclusion is that if you take K theory of R mod P, that's the same thing as K theory of R prime mod P. And this was a previous theorem of Gaber. Okay, so the next thing I will I will later explain some consequences of this theorem. So how to see, what do I mean by saying that they're close? I'll make this precise. But first I want to say just a couple of things about the proof of the theorem. And I'm not going to go into any sort of details again, but I want to make a few orienting remarks. So first of all, the proof of this theorem uses basically all of the theorems that I've quoted, and half the theorems Björn quoted in his talk. I mean, we build on a mountain of previous work. We use the Dundas-Goodwillie-McCarthy theorem. We don't use the theorem of Gaber literally, but our proof is modeled on his proof in many ways. So we don't get a new proof of his theorem really. We rather extend his proof so that it covers this new situation. We use this excision theorem that Björn mentioned. We use the results of Geisser-Levine and Geisser-Hesselholt that I mentioned earlier. I mean, just a wealth of deep material that we build on, and we just kind of shove them all together in the correct way. Plus we add one crucial new ingredient. And this is something which I'd like to explain, in fact, because it's a fundamental property of TC mod P, which had not been noticed before. And in fact, when I tried to talk to some people about it, they told me it was definitely false. Well, this is the following fact, which is actually quite remarkable, but I can explain more or less why it's true. So this crucial fact that we proved, and I'll say it like this: TC mod P is a finitary invariant. What do I mean by this? I mean that TC mod P commutes with filtered colimits. So a filtered colimit of algebras. Can always be pulled out. Why does this mean that it's finitary? Why do I say that this is a property of being finitary? What this means is if you have an arbitrary algebra and you see something happening in TC, then it has to be explained by something happening in some finitely generated subalgebra, because your algebra is a filtered union of its finitely generated subalgebras. So everything has to have some finitary explanation. Yeah, that's the meaning of this. So it reduces you to finitely generated situations, and it, again, yields nice, and it plays very well with this henselization, which is also just built from finitary information, just adjoining roots to some polynomial. Now, the reason this is shocking, well, this property is true for cyclic homology of algebras, for positive cyclic homology of algebras, because there you take Hochschild homology, which kind of clearly has this property. It's built from, again, just tensor products of the algebra, and then you have some direct sums and so on, or what we would say you have homotopy orbits for an S1 action. But it's not true for negative cyclic homology, because that involves infinite products. It involves some sort of completion process, and completions in general destroy this finitary nature, because by their definition, they involve an infinite amount of information. So, and K-theory, yeah, so I used to think of, when I first saw the definition, I thought of K-theory, and this is how it was explained to me, as a modification, of TC theory as a modification of negative cyclic homology. And in fact, in the rational case, it is just negative cyclic homology, so this is very reasonable. But here it's, yeah, so, but now the perspective offered by Nicolaus and Schulze, so I'll write down the Nicolaus-Schulze formula for TC at the prime P, so yeah, mod P, which gives a different perspective on this, which elucidates why this should be a finitary invariant. So if you want to take TC of R, that's defined as a fiber of a map from, now I never know what the correct notation is for these things, but topological negative cyclic homology, yes. Mapping to topological periodic homology, where this map, so this is defined just like negative cyclic homology, except instead of using Hochschild homology, you use topological Hochschild homology. And this is just like periodic cyclic homology, except instead of, except you use topological Hochschild homology instead of Hochschild homology. And this map is the difference between two maps. One map called the canonical map, and one map called the Frobenius map. And now here's the point. If you were to just take the canonical map and remove the Frobenius part, then you wouldn't get TC of R at all. You would exactly get, TC plus, I don't know. You would get the cyclic homology if it were just the fiber of the canonical map. Because this is the negative part, this is the periodic guy, what's left is the positive part. And now the point is, when you work with mod P coefficients, this operator, the Frobenius, is basically nilpotent in a certain sense. And so this is just a small perturbation of positive cyclic homology. And the result that you get is that in any range of homotopy degrees, you can always approximate TC by TC plus in a finitary manner. Now, to make precise this is not an endomorphism. To say what you mean by nilpotent, you work in this context called cyclotomic spectra, which is a linearization of algebras, very much akin to the one that Alain mentioned, the cyclic sets, or cyclic abelian groups, I should say. You have to pass to that broader context to make sense of this argument. But this is the essential idea here, that in fact, this guy is built out of this guy in a finitary manner. And so the finitary property for this guy implies it for this guy. But only mod P, this only works mod P, it doesn't work rationally. So yes. So the next thing I'd like to do is explain some consequences of this theorem. So, well, no, why is this theorem powerful? So before I'm not going to explain any of the deductions of the consequences, but I want to give you some ideas as to why invariance with respect to Henselian pairs is a powerful statement. Well, so first of all, the first observation is quite elementary. We're interested in p-adically complete rings, but when you have a p-adically complete ring, you can reduce it mod P, and then this is Henselian. Well, since a complete thing is Henselian, so that's exactly this. So the difference between K-theory and TC for this guy is the same as the difference between K theory and TC for this guy with mod P coefficients. So if you want to prove that K theory is always close to TC for arbitrary P complete rings, it's enough to prove it for FP algebras. Okay. Now I want to explain another technique involving the henselization, which will let you reduce the case of FP algebras to the case of smooth FP algebras, which themselves are very close to polynomial algebras over FP, infinitely many variables. And so the subject of earlier results of Geisser-Levine and Geisser-Hesselholt. So here's the trick. So if R is an FP algebra, of course you can make a surjection from R from an infinite polynomial algebra, where you just, for example, I mean, it's very silly, but you can take formal variables corresponding to the ring, elements of the ring R, and then just map them to R by sending that formal variable to the honest element R. Yeah. So it just, but really you could choose any surjection from a polynomial ring. And this is of course not going to be Henselian, but as I mentioned, you can always Henselize it, and you still get a surjection. And in fact, you can continue this process and make a simplicial resolution where you somehow preserve the Henselian property at every stage. And this simplicial resolution will be good for calculating both K theory and TC with mod P coefficients. So the K theory TC of R will be the colimit over this homotopy colimit, you should say, I guess, over this diagram. And each of these terms will be Henselizations of polynomial rings. But now the polynomial ring in infinitely many generators is a filtered union of the polynomial rings infinitely many generators. And this Henselization process was a filtered union of just adjoining a root to a separable equation. So it's always, these things are always filtered unions of smooth algebras.
Then
and so in this case,
yeah, sure. Okay.
Sorry?
You mean then you use the previous?
Yes, then you, this is, so there are no, actually there are no arguments in the paper that literally do this, but somehow this is behind this is kind of behind the idea of why we can do what we do. That in this case, in this way, you can reduce to the previous results of Geisser-Levine and Geisser-Hesselholt. Yes, using this finitary nature of TC mod P. So in fact, this kind of thing somehow goes both into the proof of the theorem and into the proof of applications of the theorem. But yeah, so that's a nice trick that we came up with here. Okay. So what are some applications? So one is that, so if R is p-adically complete, or even Henselian at P is enough, but let me not worry about that. Then, so this is an iso in homotopy for star greater than some notion of the dimension of the reduction mod P. And I don't want to get into the precise details of which dimension I mean, but for a variety, it matches up with what you'd expect. Well, yeah, more or less. You can find the details in the paper if you like. But so in low degrees, they're not going to be the same, but once you get into high enough degrees, they will start matching up. So that's one precise sense in which they're close. Here's another somewhat strange result. So if R is an FP algebra, which is local, so it has a unique maximal ideal, so it's just in Zariski neighborhood of a point, then K theory of R mod P to TC of R mod P is a split injection on homotopy groups. It's a somewhat strange statement. It's also true with the mod P to the n coefficients for all n. And you can also completely identify the complementary sum n. So you can really describe K-theory mod P in terms of TC mod P quite explicitly for a local FP algebra. This doesn't extend to the p-adic case, so this is a bit of a funny result. Now here's, I think, the most important application. So again, I'll say if R is a P-complete ring, then you can take the étale K-theory of R, and that will always map to the TC of R. And the claim is this is precisely an isomorphism. In other words, TC is the étale K-theory, so sort of at or near characteristic P. And by étale K-theory, I simply mean the étale sheafification. So I think it's worth meditating on this result for a second. So by étale K-theory of R, I mean the sheafification on spec R, étale of, R prime goes to K-theory of R prime. So if R prime is an étale R algebra. So it's just the étale sheafification in this world of spectra. So yeah, again, so it's homotopy groups would be related to étale cohomology if the homotopy groups of K-theory are related to some Zariski cohomology, for example. Right. So, but this reminds me, I actually forgot to mention one other reason why the theorem is powerful, which is relevant precisely to this result. Let me pause this explanation and go back to the previous. So another reason Henselian stuff comes up all the time, and it relates to Alain's previous comment. I'm sorry, I'm going to press the pause button on this explanation here and go back. I wanted to say another thing is that K-theory and TC, and really any non-commutative invariant, these all satisfy something called Misnevich descent, which is sort of halfway between Zariski and étale. And the local rings for the Misnevich topology are the Henselian local rings. So that's where, so that R going to the maximal ideal is Henselian in the sense that I described. So these theories satisfy a descent property which lets you reduce pretty much to the Henselian local case. Now you're precisely in the situation covered by our theorem. And so in some sense, if you know TC and you know K-theory of fields, then you know K-theory. Except you have to solve the descent, make the descent explicit. And that's actually the source of quite a number of difficulties. But let me pass over that in this talk. Okay, so I did want to mention that. But now here we're doing, K-theory is this Misnevich sheaf, but it's not an étale sheaf. But now something quite remarkable is happening here, which I want to, as I said, meditate on for a second, because we're in the commutative context here. And the definition of étale K-theory doesn't make sense in the non-commutative context. There's no, the localization is famously, even Zariski localization doesn't make sense for non-commutative spaces, of course. There's no locality for non-commutative rings. There's no way to define étale K-theory like this in the non-commutative setting. But something truly remarkable happens here. You take a non-commutative invariant K-theory, you étale sheafify it, that only makes sense in the commutative world. Then it's a non-commutative invariant again. TC. Very weird. Very weird. And I don't know how to explain why this should happen. There must be something with étale sheafification that has some non-commutative meaning. I don't know. I really just don't know how to explain this. It comes out, again, building on a series of deep works. And the special cases of this were also proved by Geiser Hesselholt, I should mention. So this line of investigation was started by them. So yeah, but it's just kind of remarkable. And I will mention that there is a similar statement when R is a Z bracket 1 over P algebra. Sort of the same phenomenon appears, but you get a different non-commutative invariant. So, and this is essentially the work of Thomason. If you take K étale R mod P, well, it's the same at least in non-negative degrees as the K1 local K theory of R mod P. So here it's a little somehow less shocking because you're taking the same invariant and just applying some operation to it. But still, that produces exactly the étale sheafification is kind of very remarkable. Yeah, so this, yeah, this I guess was maybe in this generality we did, maybe in full generality, these two results are in this second paper I mentioned with Akhil Mathew, hyperdescent and étale K theory. Right, and then another result I'd like to mention, which again, I think it's worth spending some time discussing, is that something that we did in the paper with, me and Akhil did in this paper with Bhargav Bhatt, the third paper I mentioned. And it's the following consequence. So so it has to do with this, this K1 localization, which also came up here. And I should say that this is, this is quite closely related to étale cohomology of these standard Tate twists. So Z mod P ends. So in the same way that I said K theory is related to these mu ends, well, this one's related to the standard étale Z mod P ends. So when you see this K1 local K theory, you should think étale cohomology. You should think something that behaves basically like singular cohomology. Right. So now, but what happens if you take TC of R and then you K1 localize that? Then the result is it's always naturally the same as something coming from this Thomason context, where you take the ring, well, if it wasn't p-adically complete, you better p-adically complete it, but then you invert P. So you could say this is the, well, in some sense, this is the rigid analytic generic fiber. Probably you guys don't like those words, but this is what, yeah. So it's a, yeah. And this is for a general commutative ring R. And this has an interpretation as, this is some kind of p-adic Hodge theory. Because TC is very much related to differential forms, just like cyclic homology is. On the other hand, as I said, K1 local K theory is very much related to étale cohomology. And in fact, you can recover this statement here about these spectra here, in fact, implies the Bhatt-Schulze so-called étale comparison theorem, which is an integral refinement of standard comparison theorems in p-adic Hodge theory. And it's valid in complete generality again.
You mean of the comparison between crystalline and étale? You mean no?
Well, the comparison between prismatic cohomology that they define and the étale cohomology of the generic fiber.
Okay.
So that you can recover the étale cohomology of the generic fiber from the crystalline from the prismatic cohomology, which is a version of crystalline cohomology.
Which is a version.
Makes sense in mixed characteristics.
Okay.
Yeah.
Okay.
Yes. Yeah. So now here's my question, and I'm writing it in capital letters because I think it's a big question. Is this true when R is non-commutative? So in other words, is there a non-commutative p-adic Hodge theory? This really is the Bhatt-Schulze étale comparison theorem. It's another formulation of it, you could say. You can almost go back and forth between them. So it is kind of a refined integral p-adic Hodge theory statement. Is it true in the non-commutative case, and what does it mean? So I guess the answer must be yes, of course it's true, because life is good, the universe is good, but I have no idea how to prove it, because at every single step in our proof, we use that the ring is commutative. And in fact, for the very statement, this concept of a Henselian map, I don't really know that it makes sense in the non-commutative setting. But even if it did, I don't think you'd be able to run a single one of our arguments in the non-commutative setting. So this for me is a big challenge for the future, trying to extend this to non-commutative rings. Now I should say that some of these results are known for slightly non-commutative rings. So finite algebras over commutative rings which satisfy the same hypotheses. But this is, yeah, that's too restrictive, yeah. But at least it shows that it's not completely off the mark. Okay, I think I'll actually end my talk here. Thank you for your attention.
Okay, thanks a lot. Thanks a lot, Dustin, for this great talk. And I mean, I have one sort of comment. I mean, from at the very start of your talk, when you were talking about you know, the rational case and all that, and then you were comparing TC at P at a prime and so on. And then at some point you mentioned the